Yeah, I guess I'll give a quick introduction, I guess, to Colin. So Colin's, a regular member on this contributor sync. Sammy's on the call as well. And they'll be able to walk us through some of the literature that we've been reading about how DuckDB is so fast, things like data fusion, and what are some of the planned work for Daft's new execution model, and also just generally educate us on like, yeah, what is an execution model? How do all these engines work overall? And where is Daft heading? So, Colin, I'll probably hand it over to you. Let's make sure you have permissions to share your screen. Why don't you try that real quick?
All right. Okay, can you see it? Oh, that's my calendar. Okay.
Don't
Right.
share your calendar.
Uh, okay. So yeah, I whipped up this presentation like this morning. Uh, so yeah, I'll just be going a quick like brief overview about what execution models are in general, how like different the overall concepts behind execution models across different engines. And then I'll talk about, how Daft does it really briefly as and like certain cool things that we do. And then I'll talk about how we're planning to change and improve our execution model and how that's gonna, be good for our users. Yeah. So first of all, what is an execution model, right? In short, an execution model defines how a query engine executes a different query, a given query. So the key responsibilities of an execution model are: how do I break up a query plan into individual operators? How do I pass data between operators? How much data to pass between operators? When do I want to materialize that actual data? And when and where to run an operator? Hold on. Query plan? Operator? What are you talking about, Colin? All right. A quick recap. All right. Let's say in Daft, you have this query, right? You're filtering a column B that you want greater than 7. All right, you're joining on another data frame on column A, and then you're gonna sum another column, right? So internally, your query is represented as what we call a logical plan, which is then optimized via rules like projection pushdowns or filter pushdowns, and then we transform into a physical plan. Right? A physical plan is the actual operations and algorithms we're actually going to run. And then finally, the execution engine is responsible for executing this physical plan. What does this look like, right? In Daft, we have a really nice dot explain function, which shows you each of the different steps, right? So first of all, you have a unoptimized logical plan, right? You have your source, your filter, like we saw before, and then another little branch here, which is the other source, which is the other data frame, a join on which column, what kind of strategy, and then the aggregation. And you can see in the optimize plan, right, we've included, projections here, right? These are what we call projection pushdowns. All right, we know that we only need column A for the join, so we're going to project column A from the first source. And in the last before the aggregation, we only know that we're going to use column C. So we add that little projection in there. We push it down in order to only get that column. So after the optimized logical plan, we translate it to the physical plan. This is where the different algorithms and specifics of the operators come in, right? From a source, we transform to in-memory scan because we know that data is all in memory. And we determined that because the data is small enough, we can use a broadcast join. This is how we're actually going to execute the join. So how do we translate, how do we actually execute this physical plan? So a physical plan essentially is represented as a DAG, a directed acyclic graph of operators. Each node in this DAG, to the left, you can see is an operator. In-memory scan is an operator, filter is an operator, project, join, aggregation. These are all operators. So how do we execute this, right? There's two things that an execution engine needs to care about regarding these operators. How do I invoke the operators and how an operator sends the results to next operators? And invoking the operators, there's two main ways in the literature on how to do this. There's a push-based approach and a pull-based approach. And how an operator sends results, there's different ways. There's tuple at a time, vector at a time, as well as table at a time. In terms of the data flow, OLAP engines like Daft, DuckDB, and Spark will all send results in batches, which is the vector at a time model. Um, why? Let's examine like, how other potential choices, right? If we want to send entire results per operator, like the entire result set, it's great when your row count is really small. For example, like OLTP engines, like traditional databases, right? If the rows that you want maybe like two or three, it's really easy to just send that entire result set to the next operator. But it's really expensive when you're doing large scale OLAP workloads where you have like gigabytes or petabytes of data. Um, in this case, sending one tuple at a time allows for pipelining operators. You can pass a tuple into each different operator, and you can pipeline all this computation in a multi-process
Yeah. And Colin, when you say tuple here, you mean kind of like
row.
one row almost, right?
Row.
In the table. Yeah. Okay.
Yeah, yeah,
And that's
um,
why we use a tuple versus tuple, right?
yeah,
Yeah.
yeah. So, and what's better than, one tuple is a batch of tuples. It also allows for pipelining, but our compilers, compilers love loops, right? And when you're operating on a batch of tuples, which is basically an array of tuples, we can do really crazy things like vectorize the execution with SIMD and other fancy loop optimizations like loop unrolling, for example. So now we've decided, how much data we're going to send between operators, right? So how are we actually going to get, data from one operator to another? One way to do this is a pull-based system where each operator basically calls its child operator to retrieve data, then do some processing on that data and return that data. So what's nice about this approach is that, in a single thread environment is pretty easy, right? Your operator just gets data from his child, does some processing and returns it, right? But how do you, parallelize this? Um, it's pretty hard. We use what we call exchange operators, which is what they say in the literature, which is basically um, like little stages you put between operators where you can control, um, how many instances of the next operator you want to launch, and then another exchange operator further down that consolidates all those instances into one stage, right? Another pro is that it's really easy to limit output sizes, right? The consumer, um, or maybe like the root node or something, can just say, "Oh, I only want 10 output rows," and after the first get data call, maybe it's already enough, and so we can break. So it's pretty easy to limit output sizes there. Um, the cons, however, like I said, it's harder to parallelize. You need exchange operators, which I'll show in the next slide. And each get data call incurs a virtual function lookup if you're in C++, or a dynamic dispatch if you're in Rust, for example. And so each of these incurs some level of overhead that you won't get in a push-based system. So borrowing this slide to explain exchange operators from a CMU course. So yeah, there's basically like three types. There's a gather, which gathers all the data from like your n child instances of an operator. Distribute, which launches, n different instances of an operator, and a repartition, which transforms n instances of an operator to n other instances of another operator. And so this is how we do parallelism in a pull-based system.
And how should people think about operators, Colin? Like, should they think of them as like threads, like CPU
Uh,
cores?
that's one way to think about it. You can pin, an operator to a CPU thread. But in general, an operator is basically an instruction, right? Like it takes in, a tuple or a batch of data and just transforms it and then outputs it. And then if you want to run that on a thread, that's up to you. Yeah.
And then if you want to get parallelism, then you spin up like multiple operators to have
Yeah,
them
yeah.
work in parallel.
Yeah, like multiple instances of a filter operator, for example. And then these instances can all work in parallel across threads.
Makes sense.
All right. So in a push-based system, all right, how is it different? Instead of calling, get data on your child, you actually have a parent and you're going to push data to that parent. So the producers or the root nodes of the query plan are actually doing all the work. They're controlling the uh, the the execution. The nice thing about this is that, an operator can control parallelism. For example, I have maybe like 1 million rows. I give no, 1 million rows to push data. And in this operator, I can decide, all right, I'm going to split these 1 million rows into, chunks of, 200,000. And I create 5 instances of my parent and I push data to each of these parents. So the operator can control, how many instances of the operator of the parent, for example, I want to push data into. Um, Another pro is that plans can be split into parallel pipelines that operate concurrently. And I'll give a nice visualization on what these pipelines are in the next slide. A con is, it's hard to control output sizes for limits, right? As a operator, I don't know how much output my parent wants, right? It's hard in push-based system to implement this kind of logic, right? You can probably do like fancy things where you fuse a limit to the downstream operator, or you have the parent operator somehow communicate with the child operator. But in general, it's much harder to do it in a push-based system than a pull-based system. Another con is an operator like sort merge join, where you have to iterate between two sides uh, or two tables. It's a bit harder when you have no information on what your child is going to give you.
Is it fair to say then that like in a push-based system requires a lot more like I guess you lose a lot of communication between operators, right? They aren't able to like tell other operators like, hey, like hang on, only give me 10 rows. Or
Yeah.
like, hey, hang on, like don't execute yet. My left side needs to execute first. Right. We lose a lot of that kind of
There's a lot of
communication.
that. Yeah. That's why
Right.
in systems like DuckDB, for example, and us, which do push base, all of the kind of data flow is actually organized and coordinated in a central system that can basically tell the operators about, conditions like limits, for example.
Right. So I guess the operators will like almost consult this like state object or like a provider, like, hey, like how many rows should I be processing? Right. Or like should I be executing right now? Or wait and hold on.
Yeah, something like that.
Versus in a pull-based system, the parent often has a lot of that context and will kind of coordinate its children and toll accordingly.
Yeah, exactly. Yeah.
I see.
And so, one thing I was alluding to just now about a pro of push-based system is that you can kind of split your query plan into pipelines that can execute independently. So, for example, in the original query where we showed there's a scan, project, and then join and then aggregation, there's two pipelines here. The first one is, a scan and filter project, and the next one is another scan and then a join, right? You can actually, do the scan and the first pipeline in parallel in a push-based system. The two routes, the two scans can just start by themselves, and the join, you could have for example, you could one side could be building the hash table, and the other side could be, probing the hash table, and these can happen concurrently in a push-based system. So what does Daft do? We're vectorized as with, other OLAP engines like DuckDB. We have our own abstraction of a batch of tuples called micropartitions. And we're kind of a hybrid push-pull, right? We have our own version of exchange ops, which is not really the kind of exchange I was talking earlier, but these exchange ops are more points in the program where we decide we need to materialize data, and we do this by pulling from children. For example, a sort or a join. Otherwise, it's all push, right? Each operator, for example, the project down here, it takes in a micropartition and outputs a micropartition with a centralized coordinator that manages the data flow. And one thing that Daft does pretty nicely is operator fusion. For example, if you have a scan and filter and project, we actually fuse all these operations into a single task called a partition task operation. This is great for a distributed environment because we can package multiple operators into a single task, serialize it, and then send it to a worker node to execute, which really minimizes the back and forth communication in the distributed system. So what is some of our ongoing work, right? We're actually rebuilding our execution model. Our current model doesn't do a great job of memory back pressure, and it's also pretty hard to debug an instrument. If you look into our code base, there's a lot of Python, Rust back and forth that we're doing in our execution, and there's so many points where you're just yielding stuff and you don't really know like the flow of the program that well, and because we have like exchange operators where we're fully materializing data before we do anything to it, it doesn't really help with back pressure. And so what we want is a simple streaming push-based execution with very good backpressure control, and that's all written in Rust. That's observable, easy to debug, and control seeable.
You want to explain what control seeable means a little bit?
It means when you're running your query and you control C, you want it to stop. You don't want it to like hang and like, yeah, yeah. That happens sometimes, yeah, with our current model. And it's like, oh, what happened? Where? I have no idea. Yeah. Um, and so what is our new execution model going to mean for you? Um, One, you can do streaming data. You're going to be able to do streaming data ingest into ML training or analytics. Two, overall, just faster queries. And finally, hopefully, less ooms. Hopefully we have good enough back pressure in our new model that allows us to control when we launch tasks and when to materialize data, when to spill the disk, things like that. Yeah, that's it. A lot of the information is from a lot of papers and a lot of courses as well. So credits to these people for providing the great resources. But yeah, that's it.
Awesome. Sammy, any
Uh,
follow-on words you wanted
we
to
can we
talk about
can
here?
yeah, we can have some discussions if.
Sure. Yeah, we can talk a little bit about swordfish, right? So yeah, I
Yeah.
guess like overall, right? So I guess we learned the technical bits of swordfish, but I guess what are the motivations, the primary motivations, would you say, behind swordfish? Like, what is the goal of swordfish for us?
Is that for me or for Colin? Oh,
Either.
yeah, I think there's a few things there. I think um I mean, I think the idea is like, there's push versus pull. There's a bunch of different design constraints. You can make it work with either, and they have their pros and cons, which we can go into. I think the primary motivation is what we kind of optimized earlier for was having essentially a single way to do execution and then share that across both local and a distributed context. And that's nice to, have shared code. But if you think about it, like the nature of how you would actually want to run a query locally versus distributed is actually quite different. Like the latency of the system is very different. The way you would want to handle, um, with a distributed system, like you might have contexts of like machines might go up or down. You have things where you need to deal with fault tolerance. You have things with scheduling, and with local, you kind of know how the world works already. Like you already know like everything on my laptop is on my laptop. I know how much memory I have. You can kind of assume that you can own the whole system. Versus like right now, we kind of assume that we don't have any of that. And so that makes our local scheduler just very robust, but also kind of slow.
That makes sense. Yeah. How would you say this, I guess, compares to something like DuckDB or Data Fusion, which are kind of local engines that do
Yeah.
this really well on a local level, right?
Yeah, so if you kind of like look at like the different systems, what they do for data fusion, what they end up implementing is like a what we call a volcano style. So I guess the evolution of it is like the first like pull-based engine was like volcano, right? And you can kind of think of that as like you have an iterator and you're just pulling from sources, and you can kind of think of this as like just a bunch of iterators, really. Like you have an iterator of tuples, you process it, and then the next guy ahead of you just kind of pulls from you, and so you kind of just have this big iterator chain. um, it's really simple, it works pretty well, and if you have a single core, it's pretty much like the ideal solution in my opinion. But once again, like what Colin said, is if you want to make it parallel in a local system, it's actually not too bad. What you would do is you have these like volcano they're called volcano exchangers, which is essentially like imagine a thing taking in an iterator and then outputting a bunch of different iterators, and then those iterators can run in parallel. So it's actually really hard to do things like scheduling, load balancing, work stealing, all of that's very, very difficult. So that's the design that actually Data Fusion uses. So they use iterators and then they kind of just load balance across the different cores versus something like DuckDB actually implements most of their design from a paper called like Morsel-based parallelism, right? Which is kind of like a next generation of push base that Colin again gave the overview for. And the idea for like DuckDB and the Morsel-based paper is that they kind of designed for a future that ended up not being that true, where like um, the idea for Morsel-based parallelism is that moving data between cores or between nodes on a machine can be quite expensive, right? And so back in like I think 2007, 2008, there's new architecture from Intel came out from Nehalem that essentially would design your server around these like sockets of CPUs, and each socket would have its own memory controller. And so what that means is that when you would run in a program, it could actually be on any one of the nodes in the machine. And therefore, when you access memory, it can actually be fetching it from its own like local memory bank or actually have to transfer it over from another memory bank. And that's why NUMA stands for non-unified memory access, which means if I access a random address, it could be very fast or it could be like one node away, it could be two nodes away. If you have like, let's say four, that's like kind of like in a square. So the whole morsel-based parallelism approach was that why don't we split up the work and then have the entire execution happen on a single thread that's pinned to a core, and we prohibit the scheduler from moving it. And so what that means then is that you're not going to have contention of like data moving back and forth between these cores. You actually just have your program, you have your data, you allocate it to different nodes, and then they run happily and over there. And that's kind of the DuckDB approach. I think the design that we're taking is kind of like a hybrid between the two, which is I think because we want a local runner, but we also want to reuse the local runner for distributed context, what we want to do is actually optimize for like simplicity. And also like, most of the machines we're going to run on are going to be one NUMA node. We don't really have to worry about like this data moving back and forth between sockets. So we're kind of optimizing for like, how do we be as fast as possible if let's say you have less than 32 or 64 cores, right? And that we can reuse that for like a distributed context. Was that a little too in depth?
No, I mean that makes sense. I think we had a lot of questions online actually on Twitter. They were like, "Oh, why don't you consider using DuckDB, right, as your local runner?" So I think that makes sense to add some context there.
Yeah. No, it's pretty quite interesting. Yeah, I think what the other thing too is that the way that DuckDB does its pipelining is that it's actually really effective for when you're dealing with small amount of data. Like I would say if you're dealing with less than let's say 100 gigabytes or 50 gigabytes, given this design, it's actually really good at maximizing parallelism even across your query, right? And so if you have, let's say you're processing like a 5-10 gigabyte query, you actually will get like a really fast result just because like it's able to schedule something so parallel across the whole query versus the queries that we'll probably be tackling are more 100 gigabyte plus per node. And because of that, we'll actually probably get enough parallelism per pipeline of the query. Yeah, we had a volcano exchange model before, now we're moving to like a morsel based model. Yeah,
Why? Why did the swap? I mean, that would be a complete rewrite of your
it is a complete
pipelines.
right. I think one of the things that we've kind of noticed is that for the large scale batch queries, we seem to do pretty well, but the issue is that we I think we have a lot of improvement we can do in memory stability. And so I think one of the things of not just doing things in whole partitions at a time, but actually focusing on like smaller morsels at a time can actually increase memory stability, and actually improve. I guess the main thing too is that some of the workloads we're tackling are also around like machine learning workloads where the data is very unpredictable in size. And so we have
Yeah,
had issues a lot in the last month where like one of our users had like a what was it like a 10 megabyte like parquet file, but because it was like a bunch of the same columns or same values along the column, it inflated to like
Exploded.
4 or 5 gigabytes,
Yeah.
right? And so just being able to
yeah.
handle that as well is like going to just increase stability and improve performance for our local
There's
runner.
uh, there's a whole bunch of other examples of that too, because we handle a lot of exotic data types like images and whatnot. And so, for example, if we have a Parquet file and all of it's like URLs, and we make that as one partition, the naive approach would be to like, okay, like download data from each URL to bytes, and then expand those bytes into images, and like each step of the way is like like 20x in terms of data, right? And so if we naively do this partition based, it's going to be a big explosion of memory unless you carefully tune how large your partitions are, right? But I think with a Mossel based approach, a lot of that goes away and gives a much better experience for a user to not really have to think about like, okay, how much, like what is the physical representation of my data? What are these partitions? They would have to think about that as much
Yeah.
more. Because yeah, honestly, most of our users, the way they do it is that download the images, maybe run a model or like resize the images, and it becomes very small at the end. And so if you can kind of pipeline the entire thing, then it makes a lot of sense, I think, from the execution model perspective.
Yeah, we've done I think as much as we can on the planning side, where we like try to predict the inflation factors, predict the scheduling that like how much memory we need for scheduling. But I think we've kind of hit the limits of that just at planning time. But yeah,
Can you spend more on Python, Rust, back and forth?
Yeah, I think that's mainly going to be a more quality of life thing. I don't think it'll affect, efficiency that much, but essentially what happens is right now, the execution kind of starts. For example, when you do df.collect, on the Python side, it'll call something on the Rust side, which translates a physical plan into partition tasks. And these partition tasks, the logic is actually defined on the Python side. So every single time you want to call, an operator, it goes from Rust to Python and then back to Rust. And the execution loop itself is also in Python. So in the end, you have this kind of like hodgepodge of mix and match from going back between Python and Rust doing the whole execution. And because of this, it's kind of a harder to debug and really harder to understand execution model.
Yeah, some context there too for historical reasons, right? Daft started off as a pure Python project. And then what we did was we ported the execution itself. So like the physical, like when you run something on local data structures, we ported that over to Rust. So the tail end of the workflow was now in Rust. And then what we did was we ported the planning into Rust. But then the middle portion was still in Python, the middle portion being the scheduling of the workflows and everything, because all of that was sometimes calling out to Ray, for example. And then we also have a Python runner, which runs in Python multi-threading. So that's the historical reason. But there's, at least for the local story, there's no real reason why we can't just go end to end in Rust. For distributed, if we are still using Ray, then sure, we have to go back into Python land a little bit for that. But that's kind of why today, at least, it goes from like Python to Rust to Python to Rust again.
cool. How's progress so far on the execution engine column?
Oh, spent another night diving into async Rust. I think it was pretty good. Managed to get basically what I call a streaming sync working. Basically, if you have like, basically there are stages called syncs, basically where you need to like maybe like materialize output or like control how much output you want to produce to the next operator. For example, like a limit. You don't want to, stop the world just building the sync. If you have data ready, you want to send it to the next operator as soon as possible. So I managed to get this streaming sync done, written in async Rust, which is pretty nice. And yeah, next steps is just cleaning it up, implementing more operators and testing it, and hopefully, it meets our benchmarks and maybe more.
Awesome. Yeah, super excited to see that. I mean, we should share the PR you have already.
Oh,
Yeah, I think if you post it in the Zoom chat, it will show up on the
Yeah,
report.
they just
no, not this. Oh yeah, okay, I'll post it in the Zoom chat.
Yeah, I'm pretty excited because like even for the URL simple like local URL download case, we have apparently a user who's using us on like tens to hundreds of terabytes of like loading data into PyTorch. And even something like the simple execution model, I think will already be a big improvement for them. Because they currently have to think about like okay, partition sizing and like how large are these reads that I'm doing from my Parquet files and really optimizing that, right? So even this would be already quality of life improvement for them and like way more memory stable.
cool. All right, should we wrap it up, Jay?
Yep, let's wrap it up. That was it for today.